Welcome to the Kyoto Prize at Oxford. I'm Nairi Woods, Dean of the Blavatnik School of Government. And normally, of course, we'd be welcoming you to our building that you just saw. My special thanks and special welcome today go to the Inamori family and the Inamori Foundation for this partnership which brings the Kyoto Prize to Oxford, which we treasure. And thanks to each of you for joining us here to hear from the 2019 laureates. We heard this morning from chemist CHING, and now we're about to hear from astrophysicist James Gunn, and later today we'll hear from the stage director Ariane Mnouchkine. But to start, here's a little clip that introduces you to the Kyoto Prize at Oxford. The Kyoto Prize was founded by Kazuo Inamori in Japan as a prize that would celebrate some of the best achievements in science, in the arts and philosophy, and in technology. It's about 100 million yen, that's nearly $1 million, and it's awarded in Kyoto each year. Kazuo Inamori founded this prize because of his own deep sense that we need to celebrate human achievement that feeds the human spirit. And that's what the prize does each year. It brings together excellence in all of these domains. The Kyoto Prize laureates have included people like Jane Goodall, known to most people for her work on chimpanzees and primates, Akira Kurosawa, the incredible Japanese filmmaker, or Martha Nussbaum, the extraordinary American political philosopher. Here at the Blavatnik School of Government, we partner with the Kyoto Prize to celebrate it, to bring the Kyoto Prize winners here to the heart of Oxford University, because they enable us not just to hear about the cutting edge of technology, of science, of art and philosophy, but to invite all our colleagues from other parts of Oxford, from Oxford's high schools, from other universities. The Blavatnik School of Government is a department of Oxford University with a mission to improve government around the world. It's to help people learn how to serve, to lead, to govern with a clear sense of who they're serving and why.
For too long, universities have hidden behind an ivory tower, and the commitment of the Blavatnik School is to open up the work of the university to the world around it.
Oxford University is full of brilliant researchers, teachers, students, working on some of the world's biggest challenges. What we love to do at the Blavatnik School is to bring them together with some of the leaders who are making the actual decisions and help be a portal through which all that brilliant research can actually be used and have impact. Every year here at the Blavatnik School, we're delighted to host the Kyoto Prize Lectures. I was so excited to see the latest Kyoto Prize laureates, James Gunn, the astrophysicist, Ariane Mnouchkine, the theatre director, and CHING, whose research brings us things like the OLED screen.
But both Oxford scholars and the Kyoto laureates are animated by a thirst for knowledge, an energy and a commitment always to improve, never to be satisfied. And that's what makes excellence. The University of Oxford is a deeply international institution. We have partnerships across the world. We always have. We accepted our first international student in the year 1169, and we have been welcoming students ever since. The mission of the Kyoto Prize is the very same mission that animated the founders of this university almost 900 years ago. A commitment to excellence, a commitment to using that excellence for the betterment of society.
These values of humility and service, but also of outstanding excellence, are exactly the values that we hope to reinforce in every student that walks through the door. And now for the second Kyoto Prize at Oxford lecture. And it's a great pleasure today to be able to hand over to moderate this lecture to the Philip Whetten Professor of Astrophysics, Roger Davies, the founding director of the Oxford Centre for Astrophysical Surveys, and currently President of the European Astronomical Society. Thank you so much, Roger, for leading us in this event.
Thank you, Nari. It's my pleasure to say a few words of introduction. Professor Jim Gunn is the Eugene Higgins Professor of Astronomy at Princeton. Educated in Texas, he earned his bachelor's degree at Rice University, and he has a PhD from Caltech. He's made pivotal contributions to the advancement of astronomy as a theorist, as an observer, and as an instrument builder. Even before the Sloan Digital Sky Survey, he was accomplished in all three areas. He did early work on gravitational lensing, predicted the existence of an absorption trough in the spectra of distant quasars that was later discovered in even higher redshift objects and is dubbed the Gunn-Peterson trough. He carried out sophisticated observations to determine the density of the universe and built some of the landmark instruments of the day. This is not to mention his part in the diagnosis and correction of the early problems with the optics on the Hubble Space Telescope, and his major role in the Wide Field and Planetary Camera for the Hubble. His eminence in all three areas of astronomy that such was his eminence in all three areas of astronomy that I recall when advertising new positions, colleagues would often debate for hours what kind of astronomy they wanted, what kind of astronomer they wanted. A tongue-in-cheek suggestion was, well, why don't we just advertise for someone like Jim Gunn? His work on galaxies is extensive, using brightest cluster galaxies to measure the expansion of the universe while pointing out that their evolution over cosmic time restricts their utility. He played a central role in exploring the dynamics of clusters of galaxies and successfully finding them at high redshift. Jim has a tremendous sense of humor, and in the late 80s, I remember him summarizing a conference with the intriguing title, Nearly Normal Galaxies from the Planck Time to the Present, when he quipped, "Galaxies are like people. The better you get to know them, the more peculiar they are." Jim's greatest achievement, however, is what we will hear more about today, the conception, building, and scientific leadership of the Sloan Digital Sky Survey, his bold, visionary effort to construct a detailed imaging and spectroscopic survey of 1/4 of the sky. The scientific bounty of this survey is unmatched. Thousands of papers and over 100 PhD theses have been written using the data. SDSS changed the way we do astronomy by focusing on the statistical properties of galaxies and other objects and providing open access to all the data. During his eminent career, Jim has garnered a plethora of awards. Too many to mention all of them today, but amongst the highlights are that in 1977 he was elected a member of the American Academy of Arts and Sciences. In 1983 became a MacArthur Fellow and won the Danny Heinemann Prize of the American Astronomical Society in 1998. In 1994 he got the Gold Medal of the Royal Astronomical Society. 2005 was a bumper year for awards for Jim. The Royal Swedish Academy of Sciences awarded him the Crawford Prize along with Jim Peebles and Martin Rees. The Henry Norris Russell Lectureship of the American Astronomical Society and the Gruber Cosmology Prize. President Barack Obama awarded him the National Medal of Science in 2008, and in 2013 he was awarded the Bruce Medal of the Astronomical Society of the Pacific. And of course, we're here celebrating today the 2019 award by the Inamori Foundation of the Kyoto Prize in Astrophysics. It's my great pleasure to introduce Professor Jim Gunn to deliver the Kyoto Prize Lecture in Astrophysics, Understanding the Universe and the Things that Live in It Through Astronomical Surveys.
Thank you, Roger. I hardly recognized myself from your introduction, so thank you especially. I have always found it quite remarkable that I could do astronomy and actually be paid for something I love so much, and I think many of us feel that way. But in addition, to be awarded this way by the Inamori Foundation is just especially wonderful. There have been many prizes, as Roger said. This one I think is especially special to me. I'm working on a project now which has actually been enabled by Professor Inamori's work and some of the material science that he's done. So I can't really express how deeply thankful I am to all the people at the foundation and what they've done. I will later be answering some of your questions, I hope satisfactorily. But I think now I will turn it back to Roger and we will hear my lecture. Thank you.
Thank you, Jim. So it's time to run the lecture, which was recorded in Kyoto.
I would like again to begin by thanking the Inamori Foundation and its founder for this prize and for the wonderful things it supports both in science and for the betterment of humanity. I'm very, very humble and grateful that the foundation finds me worthy of this great honor. And now I would like to tell you a little bit about my early life and career, a little bit about how the Sloan Digital Sky Survey got started, and a bit about what it has found about the universe. You saw in the introduction a picture of me with my father. I was born in 1938. My mother was a quite gifted artist, but who decided to give up art for raising me. I'm grateful for that as well, of course. My father was a geologist, and he led a team during World War II to find oil for looking at places where the Earth's gravity was slightly low, and that indicated that there might be a pocket of oil below because oil is much less dense than rock. We moved around a lot as a kid, so I didn't really have a home. We would stay in a place about a year or so as my father moved from place to place. Because of the war, he had to become an expert machinist to keep his equipment up, and he taught me that skill, and that has stayed with me since. He died when I was 12 years old, and he was basically my friend. I had few friends because we moved around a lot. My teacher, my mentor, everything, and so it was quite bad. But I was interested in astronomy from the very beginning, really for as long as I can remember. I learned to read when I was fairly young, and the first book that I really remember, and certainly my favorite book, was a book called The Stars for Sam, which was written by a man, Maxwell Reed, for his nephew, a child. And he wrote a series of science books for children, and this book was published in 1938, the year I was born, and was a sort of major formative thing in my life. Once I read this book, I never really deviated very far from wanting to be an astronomer. I didn't have very much idea what astronomers actually did, of course, but I was interested in the stars, and I wanted to study the stars, and that stayed with me the rest of my life. My father was a geologist, but he was very interested in astronomy, and now he had a child to teach things, and so he had always wanted to build telescopes, and so we built little telescopes when I was a kid. And I was so taken by the subject that after he died, I continued to build telescopes. And when I was in high school in Texas, long after he died, I built this photographic telescope, which actually resulted in my first astronomical publications in about 1965. And so here is a picture of the telescope, there it is, the 8-inch telescope, and a photograph. It was an electronic drive, as the introduction said, and also had a camera. So I was able to take astronomical photographs, and I became very, very interested at that point in astronomical imaging and the state of the art in astronomical imaging. I was an undergraduate at Rice Institute in Texas. I majored in mathematics and physics. Did some research actually very early. This was in 1965. Computers were just coming along, were not used. They were used in business a fair amount, but were just beginning to be used in science. And I was lucky enough to get in at the very beginning of that and learned how to do scientific programming when I was yet an undergraduate. Graduate school, I went to Caltech in California. I wanted to do general relativity and went to Caltech to work with a man who died the summer before I arrived. So I was not able to work in general relativity, but became interested then in, I was still interested in observational astronomy, and was very interested in the universe in the large, and I became very interested in observational cosmology. That is, the cosmology is the subject of treating the universe as a whole, as an object, to try to understand how it expands and so on. I was very interested in Einstein and general relativity, and I did some work in gravitational lensing, which was quite important at the time. And also, about the time I was finishing graduate school, quasars were discovered. And it was thought that they were very, very far away. And I did some work with a fellow graduate student, Bruce Peterson, to look at the gas between the galaxies and the universe far away. And we were able to come up with an idea that you should or should not see this stuff, depending on exactly how it worked. And there came to be something called the Gunn-Peterson effect, which was not discovered for many, many years. And actually, it was the final thing was discovered by the SDSS much later, and we'll talk a little bit about that when we get there. While I was there, I continued to build instruments, both optical and electronics. And I became very interested in a particular aspect of cosmology, of the science of the universe, and that is how galaxies are distributed in space. Galaxies, as all things in the universe, gravitate, and so they pull on one another by gravity. And as a result, their distribution in space is not completely random, because where there are a few more, the gravity is a little higher, they pull and become even more. And so these clusters are one of the largest structures that we see in the universe. I did my thesis on this topic, and investigating something called the correlation function that says how much more probable, if you have a galaxy, is it that you have a neighbor than it would be if the galaxies were just strewn in space completely randomly. And this tells us a great deal about how the universe evolves and about how gravitation works on these very large scales. This is a picture, just a 2D picture, made from photographic data. This is of the southern sky, actually. So each dot in this picture is a galaxy. And you can see that the galaxies are not distributed randomly on the sky. You see clusters, you see groups, you see many, many things. All of this is the result of gravitation pulling galaxies together. This is simply a two-dimensional picture. If you add depth, and this was an early survey done at Harvard, the Harvard-Smithsonian survey, the depths are, the distances are color-coded, and so you can see that there's really very, very strong structure in 3 dimensions. And so I became very interested in making surveys that would do a better job. The statistics of galaxies in space, in order to do this well, is to do any statistical problem. If you're doing a sociological statistical problem, you have to have very large and very carefully chosen samples. And it's the same in doing statistical astronomy. Many astronomers spend their lives studying a few objects, a class of objects, sometimes only one object. And this is enormously important for giving us the depth of understanding in single things. But my emphasis was a little different. I wanted to study whole populations, to study the statistics, and to try to figure out, in the large, how the universe came to be the way it is today. This requires very, very large telescopes with very large fields, because if you want a big sample, you have to study a lot of sky, and that means you have to look at it, a lot of it at once. So you need very sort of wide field lenses in astronomy. And this is basically the story of my career for a very long time. 60 years ago, there wasn't very much in the way of surveys. There were small survey telescopes that made maps, partly for navigational reasons, partly just to find the locations of stars in the sky. But these surveys did not record very faint objects, and they didn't really allow quantitative interpretations of things because it was just photography. Photography is beautiful, of course, to take pretty pictures, but it's very difficult to make quantitative measurements from. So all this changed actually began a long time ago, just as OLEDs began a long time ago before today. A fellow called Bernard Schmidt, who was a rather crazy Estonian optician, invented a camera that would make very, very wide fields in the sky, called the Schmidt camera or the Schmidt telescope. And there was a remarkable fellow called Fritz Zwicky at Caltech who realized the enormous impact of this on doing surveys. And Zwicky was one of the people who really pushed the idea of doing surveys. And he pushed very hard for a project to image the whole northern sky. And this was done with a big Schmidt camera that he persuaded people to build. And it ended in 1957. It resulted in a product called the Palomar Observatory Sky Survey, or the POS, which was photographs in red and blue light over the whole sky. He was a very interesting fellow. He's really one of my heroes in life. This is a picture of him, I think, in a kind of typical pose, and with the 18-inch Schmidt that he built. Zwicky didn't like astronomers very much. He thought all of his colleagues were fools. And there are many, many wonderful quotes from Zwicky, and this is, I think, one of the best of them. Astronomers are spherical bastards. No matter how you look at them, they are just bastards. But he is one of my heroes because of the emphasis on surveys. He also did really marvelous things early on. He predicted the supernova phenomenon. He predicted neutron stars. He knew that there was dark matter long before anyone else did. This is a picture of the 48-inch Schmidt that made the Palomar Sky Survey. So I want to step aside a minute from this general stream and talk about something which is very important for surveys. We have to have pictures, of course, to know where things are, but pictures don't tell us how far away things are. And in order to find out how far away things are, we need another tool. And the tool that we use is called spectroscopy. So let me spend just a few minutes talking about spectroscopy. One of the phenomena of light, of any kind of wave thing, is something called the Doppler shift. So if I have a galaxy that's moving, a star that's moving, anything that's moving, it compresses the waves, the light waves in front of it in the way it's going. So the object is moving this way. You can see that this sphere of light was emitted when the object was back here, but the object has moved, and so the waves are compressed in the direction the object is moving, and they are stretched in the way the object is moving from. So if something is moving away from you, the wavelength of the light is longer, that's called, and its longer wavelength of the light is red, that's called the red shift, and if it's moving towards you, the waves get closer together and moves to the blue, and that's called the blue shift. And we use this phenomenon to measure distances. The universe is expanding. We've known that for a long time. And what that means is that distant objects are moving away from us at very, very large speed. And the further away an object is, the faster it's moving. And there is a very simple formula that just says that the distance is some magic constant called the Hubble constant times the speed. And so if the speed is twice, the distance is twice. And that makes it very easy to sort things out in the universe. How do we do this? How do we measure the wavelength? Well, this is where spectroscopy comes in. We build an instrument which splits light into not just red, blue, and green, but into thousands of colors. And these individual colors tell us many, many things about the object, as we'll see. It makes a thing called a spectrum. The spectrum is just how much light there is at a given color of one of these thousands of colors. So the spectra of galaxies look like this. So here are 3 galaxies which are quite similar. This is the blue end of the spectrum, so this is blue light, that's red light. You can see that the objects at the top have a lot more red light. The objects at the bottom have a lot more blue light. You see several other things in here. Here you see a strong feature. That strong feature is repeated here, and it's repeated here, but it's at a slightly different place. That feature is the result of the absorption of light by calcium atoms. Well, that tells us something interesting, because it says that this galaxy, hundreds of millions of light years away, has calcium in it, the same calcium that we see on Earth. That feature is magnesium. That feature is sodium. So we see from these spectra what the object is made of. The fact that this one is shifted farther to the red than this means that it is receding from us more rapidly. That number is given by this redshift number here. We'll get back to that later. So this object is relatively nearby. This object is moving faster and is farther away. This object is moving faster yet and is even farther away. And so from this, we see what the objects are made out of, but we see more. This object is blue. This object is red. The blue comes from very young stars that were made only a few million years ago. This object has no stars that were made only a few million years ago. So these spectra tell us an enormous amount about the chemistry, about the history, and in fact, about the motion of these objects. So it tells us what the object is made of, how fast it's receding, and therefore how far away it is if it's out in the expanding universe, what are the temperatures of it, and also, if you think about it, the stars in these galaxies are in orbit about the center, and so some of them are approaching and some of them are receding. The result of that, there we go. The result of that is that if things are moving rapidly, these lines are broad, and if they're moving slowly, they're narrow. So we see not only how far away, how fast the thing is moving, but how fast things in it are moving with respect to one another. So we come back to surveys and how you do them. Photography it makes beautiful pictures, but it's not a quantitative method. And there was a lot of work, this kind of parallels what Dr. Tang told us about light emission. Astronomers don't need light emission. We need devices that record light. And there has been an enormous amount of work kind of paralleling, in a way, the work that he talked to you about light emission. Certainly photography would not have done this. We could not do a better survey with photography. We need new detectors. So in the 1970s, when I was at Caltech, Jim Westphal and I started working with a technology called CCDs that were developed at Bell Labs and that NASA were very interested in for space missions. We proposed and won a contract from NASA to build the camera, the first camera, for what was called just called Space Telescope then, that is now called Hubble. CCDs are very efficient, but at first, just as with the displays that Dr. Tang talked about, they were just too small. We needed bigger things. With the small CCDs, we built a camera called 4-shooter. This is a picture of the 4-shooter team on the 200-inch telescope at Palomar. The instrument is this big black thing in the background that you can hardly see. Here is Jim Westphal, my co-collaborator on the Space Telescope, and a small team of people, of really excellent people, who built the instrument. So we needed something bigger. So in 1986, a fellow called Morley Blount that we had been working with at Texas Instruments moved to another company called Tektronix that was interested in making very big CCDs for things that didn't work out, but never mind, they made big CCDs. And Morley showed us this is a single silicon wafer, 100 millimeters in diameter, with a single device on it. And when I saw this, I knew that here was a way to do this wonderful survey that I had been wanting to do for most of my career. So let's build a camera, put a lot of these on one focal plane, and go from there. So this was the beginnings of the Sloan Digital Sky Survey. So I worked for a couple of years designing these things. I needed to design a new kind of telescope, actually, to use it. A big focal plane with many of these, many filters to obtain color data to get temperatures over as big a range as possible, and also to work on digital storage of the data, because if we had a lot of data and it was not available in digital form, it would not be very useful. But the survey would also not be very limited without spectra. But this big CCD was also a perfect device to serve as a detector for spectrographs. But if we want to do several objects at once, why would we want to do several objects at once? Well, when you break the light into all these thousands of colors, each color becomes very, very faint. And so it takes a very, very long exposure in order to record this spectrum. A picture, there are only a few colors, and the colors are still pretty bright, and it doesn't take very long. So it takes much longer to get spectra. Just as an illustration, to do what Sloan did, suppose you wanted to take the spectra one by one with the telescope. The exposures are of the order of an hour each. 1 million galaxies, 1 hour, that's 1 million hours. At a very good site, astronomical site, there are about 1,000 dark, clear hours per year. And with no overhead at all, but there's always overhead, just making things work, it takes 1,000 years to take 1 million spectra. And I don't think any of us were quite ready to wait 1,000 years. But if you can do 500 at once, it only takes 2 years to do this. So the planning began for what became the SDSS. We had just joined an observatory, a new observatory building in New Mexico. The site seemed quite good for this, and we rather slowly and with difficulty obtained funding for this with a very large gift from the beginning from a fellow on the board at Princeton. And so eventually, the people involved in the Sloan survey were these, and I would like to bring your attention to this, a very, very large lot of work in the Sky Survey was done by the Japan SDSS promotion group. So Japan has been our colleague in this for a very long time. Why did it start then? Well, it really couldn't have started earlier because the technology simply wasn't there. We had to have the big CCDs. We had to have high-efficiency optical fibers. I'll say more about fibers in a minute. That's how we get many spectra at once. And cheap and readily available computing to handle all these things. So the goals of the survey were to image the whole sky is 40,000 square degrees. And to look up out of the Milky Way galaxy into the sort of clear part of the sky was to image the 10,000 degrees in the north, to classify and measure all the objects we could take pictures of, which was many more than we could take spectra of, about 200 million, to measure the redshift distances to the brightest million galaxies and the brightest 100,000 quasars, and to put this data together in a database that people could use. This picture you've seen before, this is just the Princeton team, but there were many, many institutions. Here is me and my wife, Jill, who played a very important role in the software in this project, a couple of our Japanese colleagues, and many others sitting in this room. So this is the site. The new survey telescope is here. You've seen pictures of it before. A nice picture taken at sunset. This is a picture of the instruments at the telescope. The two big green things are the spectrograph, and the camera, which had 30 of these big CCDs, is in the center. This is a picture of the focal plane. There were 30 of these things, and they were arranged from red, green, two infrared, an ultraviolet filter and two infrared filters, so that we got, as a star went through this, we got data in all 5 colors in about 5 minutes.
This is the distribution in the spectrum of the light from the ultraviolet, green, red, infrared, and farther infrared, and we recorded all of those basically simultaneously. Here is spectra. We did this by making a large aluminum plate, drilling holes at precisely the locations of galaxies that we learned from the imaging, plugging optical fibers in, the optical fibers come down, make the spectra, and go to the CCDs. You've seen this picture before. These are representative spectra from the survey. This is the sky that we covered. And you can see the dark is the main northern area. The green is a survey to look not at galaxies, but at stars. This was the first, the data release at the end of the first phase of the survey, 8,000 square degrees, not quite 10,000, but we did the 10,000 in the next year. Photometry for several hundred million objects. Spectroscopy over 7,000 square degrees, 1.2 million spectra, and a lot of spectra of stars. So this is a kind of step through the survey. This is a picture with these bright things are put in by hand. They are the bright stars in the sky, just to sort of orient you on the sky. And what we're going to do is just zoom in, but we could zoom in to anywhere in this area, just as we're going to zoom in here. So we get closer. You can begin to see in the center maybe what we're heading for. This is called the Whirlpool Galaxy. So from that large area over the sky, one can focus and zoom in on any object you want in that large area. And there were many, many lovely objects we took pictures of. This is a picture of a globular cluster of a galaxy that is exploding currently. This stuff in the middle is not just a mist. It's gas being blown out of the center from a major explosion in the center. A beautiful spiral galaxy. A galaxy that has just suffered a collision with another galaxy. Galaxies don't always keep to themselves. They interact in very nasty ways with their neighbors. This is the nearest galaxy to us. This is Andromeda, the Andromeda spiral. And what I want to draw your attention to is this area. We're going to zoom in on it. This is just in one nearby galaxy. So we're getting closer. We're looking at a star formation region. This is gas, which is excited by hot stars in this galaxy. We come in. We also step way out in the universe. These are nearby clusters of galaxies. This is one in Coma, Hercules. And even farther, this group here is a group of galaxies at a redshift of about 0.3. That means about 30% of the way back toward the Big Bang in the system. And this is sort of at the limit. In this was just a single pass. We also did part of the sky, in which we did many, many times, so that we could add the pictures together. And you can barely see right in here anything, but clearly when we stack things together and make very long exposures, this is a cluster at about a redshift of 1, when the universe was about half its present age and half its present size. Lots of beautiful things in the Milky Way galaxy. These are all gas clouds in the galaxy in lovely colors. Now, this is the sort of 3D distribution. You saw the movie at the beginning. This is distance. So we're looking, this is just a thin slice of sky, looking at how the galaxies are arranged. And you can see that there are filaments, there are voids, there are clusters. It's a very complicated structure. How did this come to pass? Well, in 2001, this rocket was launched, which had a satellite, which made a map of the microwave sky. This is called the cosmic microwave background, the WMAP sky. The real distribution of this, it's almost completely uniform. The brightest things in here are about a part in 100,000 brighter than the coolest things here. But it is these little ripples in the early universe that made the structure we see. So we now know, and I really don't have time to go into how we know these things. The universe began 13.6 billion years ago. The universe is full of energy. And Einstein tells us that energy and mass are the same thing, in a way. And the things that we know about, protons and neutrons and electrons, is only about 4% of this. 25% is dark matter, and the other 70% is some dark energy that we don't quite understand. So let me say, if I go to a place where there is a very slight bump in the mass distribution and follow it, what happens is this. This is a bump in everything, in the ordinary matter and the dark matter. There's a lot of pressure in the early universe. It's very hot. And that pressure pushes the ordinary matter out, but the dark matter doesn't feel this pressure. So you see the ordinary matter, which is only a small part, going out. And the universe is cooling at the same time, and it becomes cold. And what's left is around every place that there was a bump, a hill, in the early universe, there is an extra distribution of matter. Can we find that in this? Yes. If we count galaxies going out from the distance from a big galaxy, this is the correlation function that we talked about, you see that it drops off very smoothly, but there's a hump. So there are slightly too many galaxies in this ring. And this tells us that we understand pretty well what is happening in the early universe. Something else the Sloan did, because we had spectra of 1 million galaxies, we could easily look at their distributions. I don't have time to go into this in any detail, but this is colors, brightnesses, sizes, all of these things we can look at and look at the relations between. Let me call your attention to this picture. This is color versus brightness. These are bright galaxies. These are red galaxies, and let's look at that in a little more detail. So what we found was that there was a red sequence. These are the galaxies that we looked at that were red and not forming many stars, red and dead, they're called. There is a kind of green valley that separates these, and these are the blue things that are making stars like mad, even today. And so we want to understand how this developed from the microwave background and also how it developed from what we saw. We also studied the chemistry of galaxies. Stars make all of the things we are, the carbon, the nitrogen, potassium, all of these things are made in stars. And galaxies hang on to that gas when the stars explode. The stars explode, and that's how these things get out. Big galaxies, because they have high gravity, can hang on to this stuff. Little galaxies, these are big galaxies, these are little galaxies, are not so good at hanging on to it. And so there is a strong range of chemistry with mass. So the results of the SDSS, I think the ones I'm proudest of are these. We studied weak gravitational lensing. Gravitating objects bend light. And so you can study this, you can use this to detect directly masses in the universe, because you can look at how they bend light together. The baryon acoustic oscillations are what I showed you before, this pushing out of the ordinary matter. The properties of galaxies we saw. But also in the solar system, we discovered thousands of asteroids and looked at families of asteroids, chemical families, orbital families. We didn't really set out to explore the solar system, but we did. We found brown dwarf stars. These are objects which are between stars and planets. They don't burn thermonuclear fuel, and was thought for a very long time that they existed, and they were discovered actually before Sloan, but we found many, many of them and studied their properties. And of course, the large-scale structure of the universe. So the impact of this, as of the end of last summer, there were 10,000 scientific papers which used SDSS data. These papers were cited nearly 500,000 times. There were 1,000 papers with more than 100 citations, and 7 among the 100 most cited papers of all time. But it wasn't all we did. So there was also a very important legacy, I think, for the science. We insisted from the very beginning that the data would be made public very quickly. and we succeeded in doing that. And this resulted in the really natural growth of collaborations over the world using our data, both within the collaboration and without. And this openness is something that I hope it actually has become part of the sort of scientific sociology of astronomy, and it appears to be being a model for new projects. There was also citizen science. There was something called the Galaxy Zoo. We published a lot of pictures and asked the public to help us classify these things. We didn't even have any idea whether it would work, but within a day of the publication of this, we had 70,000 entries and over 150,000 people did this, worked on this as we went on. So that's sort of where we are and have been. The SDSS was finished some time ago. What do we want to do next? Well, it's very important to know that when we look out into the universe, we also look back in time. And so the universe is its own history book. If we can look out far enough, go faint enough to objects far away, we can study what the universe was like 1 billion years ago, 2 billion years ago, 10 billion years ago. And so the next step, I think, is to go out and be very faint. We know today that the universe actually is in its dotage, it's dying. This is a graph of the star formation in the universe, which is sort of the activity of things. This is a look-back time, so this is now. If we look back 10 billion years, 10 times as many stars per unit time were being born as are born today. So the universe was an incredibly active, noisy place compared to the rather quiet times of today. So we'd like to do a survey like SDSS, but with much bigger telescopes, to go much fainter, to study things far enough away that we can read this history. And it's happening. Japan is making it happen. There's a beautiful camera with 114 even bigger CCDs than we used called Hyper Supreme Cam. Satoshi Miyazaki, who I hope is in the audience and is there, oversaw the building of this. This is a photograph taken at the commissioning of this instrument at the Subaru telescope. And the imaging part of the survey is underway and more than half complete. These are pictures of the instrument. It's very big. As you can see, here is a human being by comparison. This is the team that actually built the camera, and this is the focal plane with 114 CCDs in it. This is a picture that the telescope made. I think even on this screen it doesn't do justice, but you can see that there are very, very, very many galaxies. The galaxies almost overlap. So the faintest of these galaxies came at a time when the universe was only about 1/5 its present size and 1/5 of its present age. What about spectroscopy? Well, we have to have a spectroscopic component. We're working very hard on a spectrograph for Subaru that, again, will use fibers, this time many, many more fibers, 2,400 fibers, and it will reach ordinary galaxies out to the place where the universe was doing all of this really active stuff. And this instrument has been my focus for the past some years. I said the universe makes its own history book. It's hard to read because you have to go very faint. You have to have very sensitive instruments and go very deep in order for it to work. And we're doing our best to try to read this book. We, of course, I can't say that we're completely ignorant of it because surveys, small surveys, lots of work on smaller numbers of objects is going forward, of course, all over the world, but nothing like the size of the SDSS and nothing like the size of these surveys that we're talking about that Subaru is doing. So I would like to express my thanks not only to the Inamori Foundation for this enormous honor here, but also for the privilege of working with a very large and excellent group of Japanese astronomers since SDSS days. And now, you know, I was part of running the SDSS, but they have taken over and are doing a very much better job with very big telescopes. I should also say, and I did not say really sufficiently, that you saw the list of institutions for the SDSS. I was project scientist for the SDSS, but the work I did was 1%, some tiny fraction. All of that work was done by my colleagues at these institutions, and especially wonderful for me was that the work was mostly done by my younger colleagues. So we old guys and gals who ran the survey, and we did a pretty good job, but the science was mostly done by the young colleagues, and they did a wonderful job. And that continues in the projects today, and I am enormously proud of that. I was kind of the father of SDSS, but it was my children who did the work. So thank you all, and thanks especially to the NMRA Foundation.
Thank you very much, Dr. Gunn. Please move to the center of the stage to receive flowers. James Gunn 博士、ありがとうございました。
Thank you, Jim, for that wonderful lecture. You have to imagine now the thunderous applause in the lecture theatre here at the Blavatnik School. You have shown us what can be learnt about the universe through astronomical surveys, but you've also shown us the beauty of the universe that you yourself have enjoyed exploring. So we have questions coming in from the audience, and we have a team of people taking a look at them, and they will boil them down because we have a lot of questions and ask them to you individually. But before I set them off to ask those questions, I have one question myself, which is that you mentioned towards the end of your lecture the prime focus spectrograph. This is your latest passion in astronomical surveys. What do you really hope to learn using that instrument on the Japanese Subaru telescope? Will it tell us something about dark energy?
I don't think it will tell us very much about dark energy. It will tell us a great deal about galaxies and how they evolve and perhaps even how they form. What will actually tell us about dark energy, I don't even have a clue.
Thank you, Jim. Look, I think the team are now ready, so I can hand over to Professor Martin Bureau to ask the first question.
Okay, well, thank you, Jim, for a very inspiring talk, but I think we very well about insights in the science and, of course, in your personal life. So along these lines, many, I think, will have recognized in your talk the interplay in your career between, on the one hand, serendipity, not to say luck or chance, perhaps unexpected technological advances, and on the other hand, careful planning to achieve desired scientific discoveries. So I was wondering if you could comment on the balance in your career between doggedly pursuing a specific goal, but also being opportunistic and essentially open to new opportunities.
Well, Martin, it's a very delicate balance, and people have gone both ways. I think if you look at the history of the Hubble Space Telescope, it was clearly begun much too soon because the technology was not there. It took a very, very long time, and it was a very bumpy road. Now, the Sloan was also a bumpy road. I mean, when I first saw this big CCD, I knew exactly what we had to do, but that CCD wasn't working at the time. It was simply a piece of silicon. And that was a rather bumpy road, but a much shorter one than it took Hubble to do. The real problems with the Sloan survey was that no one outside of NASA had tried to do a project this big before. And, we were scientists, not businessmen. We had no idea how much the thing would cost. and we underestimated the cost at the beginning by a factor of about 5. So we were always just, you know, at the very edge of financial extinction during the survey. It was a much bigger problem than the technical problems. I knew from the beginning sort of how to solve the technical problems. That wasn't to say they were easy to solve, but we knew, and there wasn't very much serendipity. There was an enormous amount of serendipity in the science. We had no idea we could do gravitational lensing, that the data would be good enough. We didn't know about the asteroids. We didn't know about the brown dwarfs. So I said in remarks earlier this morning in the panel discussion that my passion has been quality. You do things right to begin with. You know how to do them right, even though it may be cheaper and faster to cut corners. It's better to do them right, and that is one of my proudest accomplishments from Sloan. The other is, as I said in my lecture, that the science was mostly done by my junior colleagues, and I am a very proud father indeed.
Well, thank you very much, Jim. I think we'll have a question from Chiara Spinello.
Hi, Jim. Thank you for your lecture. It was really nice. The question is simple. If you could come back in time and change anything in replanning SDSS, what would you change?
That's a very good question, Chiara, and I really don't know the answer. So if we go back to finance, we think about this a lot. Suppose we had told our supporters that the Sloan was going to cost $80 million instead of 20. They wouldn't have funded it. Right? So I don't know what I would have done about that. It was very rough coming because we were, you know, we sometimes didn't know whether we could pay people's pay at a given time. But there were some heroes there. Jerry Oestreicher was at the time provost of Princeton, and he persuaded people that this was an exciting enough project that even though we had no idea how much it was going to cost, they should keep feeding us money. As far as and it was difficult also because there were the cultures were clashing continuously. In the end, when the science came, it was a very happy project, but it was not a happy project when it was being built. So how to change that, or whether we could have, I really don't know. As far as the planning and execution, I think we, you know, by blind luck or something, did roughly the right things at the right time. So I really don't know the answer to your question. It was a success in the end, so we should perhaps just accept that.
I agree. We shouldn't change anything. It worked. I'll hand on now to Peter Watson for another question.
Thanks, Chiara, and thanks, Jim, for the excellent talk. And of course, you've had an incredible career spanning many decades. And if you had to give one piece of advice to someone starting their own career in astrophysics today, what would you tell them?
I was lucky enough that the subject was simple enough that I could learn to do all these things: instrumentation, theory, observation. I don't think that's any longer true. So I don't quite know. I've had many students, not very many in instrumentation actually, but quite a number in observation and theory. And they have by and large been successful in their pursuits. I would stress to them that you know, you don't give up, you keep going, but these are just sort of motherhood words that everyone says. I think it is even more important now than before that you have a passion for this subject. I simply don't think it's possible to succeed without it. It never really was, but it certainly isn't today. The subject has changed a great deal. Sloan was actually a force behind this. I think, you know, when I was a young man doing the subject, most papers had one person, two persons, two authors. Now there are many, many more. And I believe that the science is enormously better because of that, because many minds together put things together that simply one person couldn't do. You know, certainly the era of the great man in astronomy is gone. There are no more de Vaucouleurs, no more Sandages. And I think that's an incredibly good thing. So collaborate, love one another, learn as much as you can over as broad an area as you can. But you don't have to have so much depth, I think, because you can put together a team in which this person knows that, this person knows that. You can talk and solve the problem. I also think that it is less important these days about credit. I talked a little bit about that in the panel discussion. The important thing, of course, is that the science gets done, not who does it. And I believe, you know, we're human beings, and we really like to be recognized for what we do. But I believe the sort of the idea that there is turf in science. This problem belongs to me. I think has disappeared and is disappearing. And I also think that's a very good thing.
Oh, thank you. That was incredibly helpful. I'll pass back now to Professor Martin Bureau. I think he's got another question lined up.
Yes, this time a question from a member of the audience. A bit tying into one of the earlier questions. The question is simply, what is the ultimate goal or aim of your research?
I don't know the answer to that, Martin. To learn as much as I can about how the universe works, I think is the ultimate goal. And I don't have any preconception that I will completely understand anything by the time I die. And I'm an old man, and that won't be very long in any case. But science is, astronomy is like any other science, an edifice which grows by the addition of little blocks. And so I want to add as many of them myself as I can and be proud of what I do. But I don't think I have any particular goals of understanding X, Y, Z, or A, and B, just to try to understand the whole picture as well as I can. And I think it's probably the goal of all of us. And
thank you very much. Back to Chiara.
Jim, another question from the audience. Will human be able to come up with a theory which is perfectly able to connect quantum mechanics and general relativity? And when do you think this will happen?
That question is very, very easy to answer. And that is that I understand the general relativity. I used to understand it very well. I never understood quantum mechanics very well. And so the probability of my coming up with the unification of quantum mechanics and gravity is zero, and especially at my age, because I don't do theory anymore. The goal is certainly there. People have been working on it a very long time. My feeling, having watched this now for decades, is that we're not very close to an answer. And I doubt very, very seriously that I will see the answer in my lifetime. I hope you will, but I don't think I will.
Thank you, Jim. Peter?
Thanks. One last question from me. So you had a pivotal role in developing SDSS. What do you think the next similarly revolutionary instrument would be?
Oh, well, that is an easy question, actually. You know, with SDSS and also with the current survey, Hyper-Supreme Cam and PFS, we are doing imaging. After the imaging is done, we choose targets and we do spectroscopy. But wouldn't it be lovely to have an instrument which, when you were doing the imaging, did spectroscopy on each and every object that have sufficiently large resolution to do? And they're being developed, MKIDs, various other things. We will see those, I think, again, probably not in large instruments during my lifetime, but certainly in yours, they will come. And they will really revolutionize the way we do things, because this data will be gathered at once. One has the ability now to go very, very much fainter than before. And certainly this is in the optical and the infrared. In other bands that mostly you have to do from space, I'm afraid the answer is just bigger and bigger telescopes. And one then becomes, you know, the budgets become large fractions of the GNP of nations. And whether we decide to spend money on astronomy that way is something that we'll have to decide at the time. But it will be difficult, I think.
I mean, we can certainly hope we'll build more telescopes in space. So that's all for me now. I'll hand back to Professor Roger Davies again.
Hello, Jim. Again, you have shown us how technology revolutionizes astronomical surveys, but you've also shown us how SDSS changed the way we do astronomy more or less forever. So when you were a young man and when I was a young man, we used to go to the telescope regularly, have long, dark, cold nights at remote sites. And that is an experience which is much less common amongst young researchers these days. Do you miss it?
Oh, yes, I miss it very, very much. Because of the 200-inch telescope freezing is something that I remember with enormous fondness. But nevertheless, the science is very, very much better off, I think, for the way we do it today.
I completely agree with you, Jim. Let's go back to Professor Martin Bureau.
Yes, thank you, Roger. I would like to remind the audience that they can type questions in the Q&A box. We still have a little bit of time. In fact, I was going to expand, Jim, on the same topic Roger touched upon, and you touched upon already, which is that SDSS has had a tremendous impact on what we might call the sociology of astronomy, ranging from how we decide on research projects to publications to career progression, you know, how we assign credit to people. So I wonder if you could comment a little bit more on this, expand a little bit on your earlier comments on this. Thank you.
Yes, well, as I said, I was not used to large collaborations at the beginning. I had really never, well, I was involved in Space Telescope, which became Hubble. And it was a large collaboration, but it was a construction project at the time. So it wasn't a question of doing science with lots of people. And I had severe misgivings about this because I had sort of seen how it works in physics with large collaborations and people being forgotten and swamped and all of these things. And to this day, I don't quite understand how we handled it in Sloan, but in the end, it worked out very, very, very well. And the young people who were bright, who worked very hard, who did all the work, were rewarded for this, even though they were hardly ever on a paper, you know, with fewer than 50 other people. Partly the word gets around, they travel, they talk, I don't know. But it's worked very well, and I think continues to work very well, you know, outside of Sloan, because these kinds of collaborations go on now. And as I said, I believe the subject is just enormously richer for this, and also enormously better science gets done, just because the more people you have thinking about a problem, the more likely you're to come up with a reasonable solution for it.
Thank you very much. Chiara?
So, Jim, in your opinion, what is the most important astronomical discovery in this century? Not necessarily SDSS, but overall in general.
I don't know, there have been many. Perhaps, certainly the most surprising, and perhaps the most important, is the discovery of dark energy. And before that, I think the discovery of dark matter. The discovery of dark matter, I think, was also sociologically very important, because we were a very cocky species when I was coming up, and we thought we knew what the universe was made out of, and we were dead wrong. There is some carbon and some hydrogen, and even more major than that, of course, is the energy content of the universe, which we don't understand. And they're enormously important problems. I think certainly during your lifetime, we'll understand dark matter. I hope we'll understand dark energy, but I don't think we'll understand either of them during mine. But it necessitated a broader view of the universe, and the realization that we don't understand things quite so well as we thought, which I think is a very important step.
Thank you. Peter?
Thanks, Chiara. So one from Emily in the audience. If you were starting again in this field, you could just start your career over again, where would you begin? Would you still stay with the SDSS and the Subaru cameras, or would you pick a new field to get involved with?
Well, I'm sorry. Is this, Peter, a advice to the young, or sort of a question of how I got here?
Oh, a question of where would you go?
Where would I go if I were doing it again?
Yeah.
I don't think I would have changed very much. I had this rather unusual collection of skills, and I'm by and large happy with the way it went, not necessarily, with myself as a human being, because I think, I was not at all interested in society at the beginning, and I'm very much more now actually with my science. I'm pretty happy with the way things went. Now, as far as advice to the young, well, we talked about that a little bit before. I'm not really sure. I think you need to understand your own strengths and your weaknesses and go there. And that will be a very different path for everybody, I think. A very individual thing.
Oh, thank you very much. I think we've got one more question from Martin Bureau, so I'll pass back to him now.
Okay. Well, Jim, perhaps on an end note, perhaps you could tell us which discovery you would like to be seen in this 21st century. So, which big question would you like to see answered?
Well, we talked about three: unification of quantum mechanics and relativity, and perhaps even, questions of grand unified theories and such. My impression is that particle physics now is in something of a mess, because we know the standard model can't be the whole answer, but we don't know where it's going. One hopes that when that theory comes, we will understand dark matter, because it's got to be a particle. the understanding of dark energy may come from the unification of quantum mechanics and general relativity. I don't know. But those, to me, those, at least in the areas of cosmology, are the big questions. I'm not very sanguine that they're going to be solved very soon.
Thank you very much, Jim. That sounds like a good note to draw the discussion to a conclusion. You have given us an enormous insight into how you go about conducting a huge astronomical survey. You were the leader of the team that first saw a redshift survey of 1 million galaxies. You've shown us what we have learned about the universe as a result of that and given us a terrific lecture. So I'd like to thank my co-moderators and I'd like to thank you very much for a wonderful lecture. And I'll now hand over to Neri Woods to make a few closing remarks.
Thank you very much. Really, all I want to do is to say a huge thanks to Professor Roger Davies and his fantastic team. It's lovely to see Oxford scientists working in such brilliant teamwork, and for moderating the second of the Kyoto Prize at Oxford series. A special and a particular thanks and congratulations to James Gunn for winning the 2019 Kyoto Prize, but also for answering every question with such depth and such inspiration to all those listening. And last but certainly not least, thank you to each one of you for joining us today. And let me just close with a slide of the details of the remaining Kyoto Prize lecture, which will take place this evening. Thank you so much for joining us, and I hope you'll come join us in person at the Blavatnik School of Government next year.